packet can cross a network in a fraction of a millisecond. An imprecise explanation can waste an afternoon. EVPN, VXLAN, multi-homing, and tenant isolation do not replace ordinary forwarding. They depend upon it. The rejected assumption is that successful application traffic proves the path is understood. It does not. The core learning is exact. A service can be trusted only when we can name every lookup and every boundary in its packet walk. We shall begin with an Ethernet frame, identify where bridging ends and routing begins, and finish with evidence another engineer can reproduce. Here is our agenda. First, we shall separate the frame, seen by Ethernet, from the packet, seen by IP. Second, we shall examine how a bridge learns a source and looks up a destination. Third, we shall identify the boundary created by a VLAN or bridge domain. Fourth, we shall see how ARP or neighbor discovery finds the next link layer address. Fifth, we shall enter the correct VRF, perform a longest prefix match, and select a next hop. Finally, we shall assemble those decisions into one observable, end-to-end packet proof. The word packet is useful in conversation, but imprecise in diagnosis. Application data may sit inside a TCP or UDP segment. That sits inside an IP packet. On Ethernet, the IP packet sits inside a frame, with source and destination MAC addresses. A bridge principally forwards the outer frame. A router removes that frame and makes a new decision using the IP destination. A tunnel adds another outer delivery context around the original object. At every boundary, ask which header is currently authoritative and which header is merely being carried. An ordinary learning bridge observes the source MAC address of an arriving frame and associates that address with the ingress port within a VLAN. It then examines the destination. A known unicast destination maps to a particular forwarding port. An unknown unicast destination has no usable forwarding database entry and is normally flooded within the permitted bridge domain. Broadcast is also replicated within that domain. Notice the asymmetry. Learning uses the source, while forwarding uses the destination. And the practical lookup key is not merely a MAC address. On a VLAN-aware bridge, the VLAN must match as well. Flooding does not mean sending a frame through every interface in the machine. The frame is first classified into a bridge domain, or VLAN. Replication is limited to eligible members of that domain, subject to forwarding state, port isolation, storm control, and other policy. The arrival port is not an ordinary destination for its own flooded frame. This boundary matters enormously in overlays. BUM traffic means broadcast, unknown unicast, and multicast, but each category still has a defined replication set. When diagnosing unwanted traffic, do not ask only whether flooding occurred. Ask which domain supplied the replication membership. These terms are related, but they are not synonyms. A VLAN identifier is carried or inferred at an Ethernet attachment. A bridge domain is the Layer 2 forwarding and flooding context. An IP subnet describes an addressing relationship. A VRF selects a distinct Layer 3 forwarding table. A tenant is an administrative and security concept that may contain many bridge domains, subnets, and VRFs. Implementations often map one VLAN to one bridge domain, but that convention is not the definition. Before following a packet, write down the actual Layer 2 and Layer 3 contexts, not merely the names used in configuration. Before a host can build an Ethernet frame, it chooses a next hop. If the IP destination is considered on link, the next hop is the destination itself. Otherwise, it is normally a default router. The host must then discover the next hop's link layer address. IPv4 commonly uses ARP to map an IP address to an Ethernet address. IPv6 neighbor discovery performs address resolution and also discovers routers and tests neighbor reachability. The resulting Ethernet destination belongs to the next hop on this link. It need not belong to the final IP destination, several routed hops away. A router terminates the incoming Layer 2 delivery. It validates and removes the ingress framing, selects a forwarding context, and looks up the IP destination. It decrements the IPv4, TTL, or IPv6 hop limit, chooses a next hop and egress interface, then constructs new link layer framing for the next link. The source and destination MAC addresses therefore change at each routed Ethernet hop. In ordinary forwarding, the source and destination IP addresses remain the end-to-end identities. Network address translation is a separate mechanism and must not be smuggled into the basic routing model. A route lookup begins by choosing the correct table. The ingress interface, policy, or tunnel context commonly identifies a VRF. Within that table, forwarding applies longest prefix match. Among covering prefixes, the most specific match wins. A /24 therefore defeats a default route for addresses it covers, regardless of how attractive the default route may otherwise seem. The selected entry identifies a next hop, an egress interface, or a recursive object that must itself resolve. A route in another VRF is deliberately invisible unless policy has leaked it. Always record both the prefix and the table in which it was found. Equal cost multipath allows a forwarding entry to contain several eligible next hops. Implementations normally hash-selected packet fields, so packets belonging to one flow remain on one path, reducing reordering. This does not promise equal byte counts, because flows differ in size and duration. It does not promise that the reverse flow chooses the same links, nor does it make an unresolved or failed next hop valid. When membership changes, some flows may move. For overlays, inner and outer header choices affect entropy. The correct proof combines the installed next hop group, the hash inputs documented for the platform, and observed traffic across members. Routing can be entirely correct, while packets fail because they are too large. A link MTU is the largest IEP packet that link can convey. The path MTU is the smallest link MTU along the complete path. Encapsulation adds outer headers, so the underlay must carry more bytes than the original tenant packet. IPv4 may fragment in some circumstances, although designs commonly try to avoid it. IPv6 routers do not fragment transit packets. An oversized packet is discarded, and an ICMP packet, too big message, is returned. If that feedback is blocked, small tests pass, while larger applications mysteriously stall. Now walk one ordinary packet. The application supplies a destination IP address. The host decides whether that destination is on link and chooses either the destination or a router as its next hop. A RP, or neighbor discovery, supplies the next hop's MAC address. The host transmits a frame. Each bridge learns the source and forwards or floods according to the destination within the VLAN. At a router, the frame ends. The router chooses a VRF, performs longest prefix match, resolves the next hop, decrements the hop limit, and builds a new frame. This repeats until the destination is on link. Configuration describes intent. Observation supplies evidence. Confirm that ingress counters increase on the expected attachment. Verify the classified VLAN or bridge domain and the forwarding database entry. Verify the neighbor entry that binds next hop IP to link layer address. Verify the route inside the correct VRF and the resolved next hop group. Confirm that software and hardware counters agree where separate forwarding planes exist. Finally, capture the packet at useful boundaries and inspect the actual headers. Positive proof shows the expected packet. Negative proof shows that it did not appear in a forbidden VLAN, VRF, tenant, or egress port. The core learning is this: name every lookup and name every boundary. At each stage, identify the object, the context, the lookup, the selected next hop, the rewrite, and the evidence. These are not merely study questions. They are a repeatable fault isolation method. VXLAN adds an outer delivery context. EVPN distributes forwarding information. Multi-homing coordinates several paths. None removes the ordinary packet decisions we have followed today. Do not accept the packet walk-on trust. Choose one flow. Capture it at two boundaries. Inspect the relevant tables and show where every address and header changed.